Swayamprabha. Digital India. Educated India.
Greetings, welcome and welcome again to this course on CFD. So far we have seen different discretization procedure, particularly finite volume in detail, turbulent flows and modeling, boundary condition implementation, and how to arrive at generalized discretized equation. This week class we will focus on how to get a solution of linear equations. There are two methods in particular, direct methods and iterative methods. In direct methods we are going to see three methods: Gauss elimination method, a specialized form of Gauss elimination method called tridiagonal matrix algorithm, LU decomposition. We will also talk about 5 different methods under iterative methods. Then there is a procedure called preconditioning. If the matrix is ill conditioned, difficult to get a solution, then we do a procedure called preconditioning. We will talk about different procedures available under preconditioning. By now we know whether we follow finite difference or finite volume method. Discretizing the governing equation will result in system of algebraic equation. These equations can be written in matrix form as A into X equal to B, where A is a coefficient matrix, X is a column vector of unknown and B is another known matrix. The coefficient matrix A, it may be banded or sparse. For sparse, it is sparse because we use different structural grid or unstructured grid. We follow different discretization procedure. For example, when we talked about finite volume procedure for convection, we have different procedure: pure upwinding, quick scheme or central type linear approximation, and we have a different procedure for diffusion term. So, if we put them together, then it may result in not a banded structure. And we also observe the matrix coefficient matrix has many 0 elements. So, solving such a system is very important because it affects solution accuracy and it takes computational time enormously. There are two approaches, one is direct method, other one is iterative methods. To understand this, knowledge on matrix will be very helpful, which you would have studied in your basic undergraduate program. Matrix algebra in terms of Cramer's rule, eigenvalues, pivoting, singular matrix, rank of a matrix, all those things will be very helpful to understand the solution procedure. We will now focus particularly on direct methods. We are going to talk about 3 methods: Gauss elimination method, tridiagonal matrix algorithm and LU decomposition. In iterative methods, we have Jacobi methods, point or line Gauss-Seidel method, point or line successive over relaxation SOR method. Then there is an alternative direction implicit ADI method. Gauss elimination method, it has basically 2 steps. One is a forward elimination, the second step is a backward substitution. In the forward elimination, the method reduces a given set of n equation into an equivalent triangular set. So, the coefficient matrix at the end of the forward elimination step will result in the form of what is known as a upper triangular matrix. By doing so, at the end the last equation will have one unknown and the unknown is directly computed. Then the remaining unknowns are computed by a step called backward substitution. This method is good if the number of equation is less and when the coefficient matrix is sufficiently simple. And for large number of equations to be solved, which is the case for example say 3D calculation, or if the matrix is sparse, then this procedure of Gauss elimination is not economical. It may also lead to erroneous results. Number of floating point operation required in Gauss elimination method is of the order n cube, and we have today most of the programs are parallelized to get results quicker or turnaround time for computation to be as short as possible. In such case, we should have a matrix inversion procedure also parallelizable. The Gauss elimination procedure is not parallelizable. Let us look at in detail. A set of linear algebraic equation is shown here, where A as well as B are constants. The same equation in the form of matrix is written here. The coefficient matrix A, it has elements A11 for example all the way up to ANN. Then unknown column vector x from x1 to xn. Then on the right hand side you have a known column vector b1 to bn. So, coefficient matrix A has n by n size and column vector unknown column vector has a size n by 1, and the final and right hand side B matrix has a size n cross 1. In simple form it is written as A x equal to B. We will see the procedure for 3 by 3 combination matrix. So, here it is elements are given A11, A12, A13 for example, and column vector is given unknown x1, x2, x3. On the right side you have B1, B2, B3. So, in step 1 and 2, because there are only 2 steps in this, because you have only 3 by 3 matrix. Step 1 and 2 involve pivoting, and that is stage is called forward elimination. So, in the first step A11, A12, A13 is not altered, whereas the second row and third row are altered, and the altered coefficient is written with a superscript in the bracket 1. Correspondingly, coefficient matrix on the B is also altered, and that is also written here as B2 superscript 1 and B3 superscript 1. Now, you do the pivoting for the second step also, and you can observe the third row is now altered as A33 with a superscript 2 standing for that it is a second time pivoting. Correspondingly, coefficient B also is changed B3 with a superscript 2. Now, we can immediately observe the coefficient matrix, original coefficient matrix A is now reduced to upper triangular matrix as shown here. The last row for corresponding unknown x3, and you can immediately get x3. Then we follow what is known as a backward substitution in this direction to go x1. So, in forward elimination we do row manipulation. We also have a procedure what is known as a augmented matrix, and which is represented here as A is the original matrix with the line, and B is the element to use for augmentation. So, A11, A12, A11, A1n all the way up to ANN, that coefficient matrix is now augmented by including right side B matrix, and that is shown in this. Now, we perform elementary row manipulation, reduce that augmented matrix to U upper triangular matrix with every time you get new value for the coefficient matrix B also. This what is shown here is a skeleton of the program used to perform this operation. So, do I is equal to 1 to n minus 1 and k I plus 1 to n, you have rho of k is equal to rho of k minus, this is the pivoting operation, and you end the do loops. Now, we do the backward substitution because all now become upper triangular matrix, and you can immediately recognize the last row of that matrix u n n is the only element, all other elements are 0. So, if you write the equation corresponding equation for this, it becomes u n n x n equal to b n prime. So, we directly get x n, then we use that to obtain other unknown coefficients in the reverse order from x n minus 1 to x 1. This is achieved by what is known as recursive relationship, and that is what is shown in this formula. X I is equal to b I prime minus summation j I plus 1 to n u I j x j by u I I. Now, because it is a recursive relationship, it is also easy to program, and this is a structure of the program which you might use to get the backward substitution. We explained the Gauss elimination procedure with the help of a simple matrix as shown here. So, 50, 1, 2, 1, 40, 4, 2, 6, 30 are elements of that matrix. X 1, x 2, x 3 are column vector unknown values equal to the right side 1, 2, 3. There is an exact solution available for this matrix system, and that is also listed as shown here as 0.016, 0.041 and 0.091. We explain Gauss elimination procedure for this system in the next 2 slides. Coefficient matrix is written along with augmenting considering the right side value 1, 2, 3 as shown here. So, we do few arithmetic operation and we decide to have a 2 decimal accuracy. So, start with the augmented matrix as shown here. First operation, perform multiply the first row by minus 1 by 50 factor and add to the second row. So, second row first element is 1, first row first element is 50. We want to make the second row first element as 0. So, to do that, we multiply the first row by minus 1 by 50 and add to the second row, then that will result in 0 for the first element in the second row. Similarly, the third row, the first element is 2 and we have to make it to 0. To achieve that, we do this operation, multiply the first row by minus 2 by 50 factor and add to the third row. So, if we perform these 2 operations on this matrix including the augmented column, then it will result as shown here. The first row remains the same, second row first value goes to 0, that is the intention. Similarly, the third row first value goes to 0, that is again the intention, and remaining values gets adjusted because of this operation. So, 40 becomes 39.98, 4 becomes 3.98 and 2 becomes 1.98. Similarly, for the third row, because we are following accuracy up to 2 decimals, we have written here values up to 2 decimals. Please recall, in the Gauss elimination we have to make the matrix upper triangular. So, the lower part has to go to 0. That means, in this case we have to make the second element third row also 0. So, to do that, we have to perform one more operation as given here, multiply the second row by 6 by 40 and add to the third row, and that will result in the second element in the third row as 0. The remaining values gets adjusted as shown here. So, original matrix which is displayed here gets converted into upper triangular matrix as shown here. So, 50, 1, 2, 0, 39.98, 3.98, 0, 0 and 28.41 and 2.67. So, we do first forward elimination and then backward substitution. The matrix is reproduced here. So, backward substitution, we start from the last row. So, last row is 28.41 into x 3 equal to 2.67. So, if you perform you get value as 0.0938. We compare this against the exact value, that is 0.091, and the error is approximately 2.2%. We do the back substitution. So, second row will give you the x 2 value and first row will give you the x 1 value as shown here, and corresponding deviation percentage with respect to the true value is also shown here. So, they are within acceptable level, that is 2 to 2.5%. There are possible problems in Gauss elimination. 0 may be there on the diagonal element, and when we perform floating operation we may end up a statement like dividing by 0. And we have observed there are many floating points operation, in other words flops, and which may cause numerical precision problem, because you are handling so many operations and every time you are approximating, and any error introduced at any stage will propagate and finally you may get an erroneous result. And system may be ill conditioned for the matrix condition determinant A is approximately or very close to 0 situation. There are solutions available for these kind of problem. One, you can carry more significant figures. So, instead of limiting to 3 decimals, you can use a double position which handles up to 16 significant position after decimals. Then it is also possible to have different pivoting strategy. In the next few slides we are going to talk about different pivoting strategy. So, pivoting we have 3 different types. First one is what is known as a row pivoting. It is also otherwise called partial pivoting. It is good for many situation. At every step I we find the max corresponding to k I to n, and all other elements are adjusted for that maximum value. So, move corresponding row to the pivot position. It avoids any 0 element, because you are finding out maximum value and 0 is automatically avoided, and that helps to avoid dividing by 0 error, and it keeps number of small and minimizes round of error, and it uses an equation with large element value to find x I. It maintains diagonal dominance. We already seen why it maintains diagonal dominance. The row pivoting does not affect order of the variable. So, this is very important, because we are dealing with the matrix, we are dealing with the unknown coefficient, it should not change the order of the variable, and it is included because of these properties in any good Gaussian elimination procedure. So, normally we do only row pivoting. Next pivoting is a column pivoting. For j 1 to n, get the largest value. So, this is like row pivoting. Instead of row we consider column, and reorder remaining variables x j. This column pivoting results in changing the order of the unknowns x I. Hence, it may lead to complexity in the algorithm, and this is usually not preferred. There is another procedure, what is known as a complete or full pivoting, where we perform both row pivoting as well as column pivoting. If coefficient matrix A is symmetric, then we need to pay attention to preserve symmetry while doing this kind of pivoting. So, in today's class we have particularly seen Gauss elimination in detail. Tomorrow's class we will see a special form of Gauss elimination procedure, what is known as a Thomas algorithm for triangular system of matrix. Thank you.